skip this part. All right, well, hi everyone. Welcome to our first Calgary RR user group session of 2022. Before we get started, I'd just like to thank our sponsor, our consortium, for basically granting small funds, granting small group funds so that we can continue hosting meetings like this. Today's presentation I'm very excited about. Please welcome Cherri. Cherri Zhang, she is presenting today on, I know the formal presentation was the validation of the underlying constructs of survey instruments. But she did give me a peek at her presentation, and I'm quite excited because it's a little bit more on, factor analysis and measurement invariance. So that's really cool. So thank you, Cherri, for taking the time to share that with us today. Some background on Cherri before we get started. She graduated with a bachelor's degree in nursing from the U of C here in Calgary, and has a master's degree in health science from the University of Tokyo. She has 3 years of experience working as a data manager and an analyst in different departments at the University of Calgary as well. She's passionate about global health and coding. And as I love this little piece of trivia she has, she is on her way to earning a black belt in Taekwondo. So that's really awesome. Cherri today has let us know. We'll take your questions. If you wanted to throw them in the chat, please go ahead. Otherwise, if you're feeling brave as well, feel free to unmute or raise up your hand, and we'll try to get Cherri to answer them between breaths. So without further ado, thank you, Cherri. The floor is yours. And I can't quite hear you. Right. I think you're still there.
Okay, yes, there we
awesome.
go.
Sorry about that.
All right, so good evening, everyone. Thanks for coming despite your busy day with work. And so like John has mentioned, will be talking about factor analysis and measurement invariance in R. So this topic was actually quite new to me last year. I spent almost half a year doing this, and then eventually writing up a manuscript, and which is under review right now. So I am still quite new with R as well. So I'll try my best to answer your questions. And oh yeah, there we go. So yeah, as Zhang mentioned, so I have a bachelor's degree in nursing. I've always been interested in public health. So I decided I want to do a master's degree there. And because at that time I really want to get out of Calgary, which I still do. So so then I went to Tokyo, and after that I've been working at the University of Calgary in department critical care medicine, and now I am working for department psychology. And so today we'll first talk about health and behavior inventory, which is the survey question that the factor analysis and measurement invariance is based on. I will describe a little bit about the demographics of the data that I've used. And then we'll go through what is factor analysis, measurement invariance. And then I will show some R codes. Unfortunately, we cannot run these codes together because it will take hours to get output. And obviously we don't have the raw data. And then we'll just wrap up after that. So in psychology, we tend to give a lot of questionnaires on different things like psychosocial measurements, or eating, dieting, eating health habits, sleeping habits, things like that. So for this factor analysis is based on these 20 questions right here. So for the first 11 questions, it asks us about any sort of the cognitive symptoms after concussion. So we would distribute these to kids who has sustained concussion. And so it asks them about their concentrating, memories, problem solving after concussion. And then from 12 to 20 is more of the physical symptoms. They have headache, feel dizzy, blurred vision, blurred vision, and things like that. So for my study, we had about 600 kids who had 600. We enrolled a total of 1,000 kids. There were about 600 of them that had concussion. So we call them mild traumatic brain injury. And then we had about 350 kids who had orthopedic injury as a control. And these questionnaires were admitted to kids from 8 to 17 years old. Each question is based on a scale from 0 to 3. So they will be asked, for example, do you ever get confused? They'll be say never, rarely, sometimes, or often. And they were distributed, and these questions were answered at 10 days, 3 months, and 6 months post-concussion, ideally. And both the child and their parent would answer these questions separately. And so from previous studies, this survey has been used for quite some time. And from previous studies, they have an idea that the first 11 questions answer this cognitive symptoms. And from the next 9 questions, it's about somatic symptoms. So here is already an idea of what factor analysis is basically we want to group these raw questions into a common total score. So that is easier to do regression analysis later on, because you don't want to be using these 20 questions as covariates, because that gets very complicated and confusing. So yeah, so we want to be able to group these raw questions. And wait. Okay, yeah. So just about the demographics. So in the end, yeah, so we had about 565 kids with mild traumatic brain injury, and then 289 kids with orthopedic injury. The median, the mean age was about 12.5, and then male, female is about 40 to 50, like we're relatively half and half. And the most 70% of the kids were white, and then we had some indigenous Asians at 10%, yeah, Hispanic, Black, and then other race, mixed race. And then for parental education, we see that here. So yeah, about more than 50% has a more than high school degree here. And then these data were collected from Calgary, Edmonton, Montreal, Ottawa, and Vancouver at their respective children's hospitals. And here, 70% of the kids never had concussion when we enrolled them. 20% of them had previously had 1 concussion, and yeah, 12 of them had more than 2. And most of these injuries 50% of these injuries come from fall, and yeah, 30, and then 20% comes from being struck by an object, and then being struck by a person. And majority at 80% are sports and recreation are related. And yeah. So before we dive into factor analysis, what you can look at is to see the correlation between each question. So this item means the question. So we had 20 questions for our survey, and we want to see how correlated question 1 is with question 2 and question 3, and so on. So this is something called the Polychoric correlation that you can do in R. And you use the library itself as psych, and then you just say Polychoric and then your data frame. So with my data, it's just ranged with each row representing an ID, so a kid, and then they will have 20 questions across. So the scores for the 20 questions. And then after that, you just find the ROH, and then you'll get this. You still have to do a little bit of plotting, but basically you'll get something like this. So here we see the diagonal line here. This part, the bottom is the parent ratings, and here on top is the children's ratings. And we can already see that question 1 to 11 are more correlated than the rest of the questions. This is already showing that perhaps this is one factor, which in my previous slides, I've showed that the first 11 questions are cognitive symptoms. So this is already evidence that our guesses are correct. And then here from the bottom, question 12 to 20, we can see these are more correlated than the rest. And for the children's, it's not as clear. We still can see that question 1 to 11 are more correlated than the rest. But then for the here from question 12 to 20, it's getting harder to see that correlation. So this is why we want to do factor analysis to confirm whether question 12 and 20 can be grouped together. And so I'll talk about this last part after I talk about this next slide. So then for factor, there's two components to factor analysis, exploratory and confirmatory. For exploratory, basically you just want to explore how many factors there are because when you don't know. And so there's two kinds of rotations you can use. Orthogonal means that the factors cannot be, the factors themselves, the ones that I had before, the cognitive and somatic, they are not allowed to correlate together. And then for the oblique rotation, that means the factors themselves can correlate. And you want to look at each question that loads onto a factor more than 0.3. So if they're less than 0.3, then we can just ignore that. That means that question is not loading onto that factor at all. And then each factor will also, you will also get a value for each factor as well. And you want to keep the factors that's greater than 1. So for, and then you also get something called variance and for each factor as well, which will, so that is when each factor explains the percent of total variance. And also you'll get a total variance as well for all the factors. So when I did my exploratory factor analysis, and here, this is the code for that. You just have to do, still it's the same library. And you have EFA as for exploratory factor analysis. And you say factor analysis, R is the ROH that you got from here, from the Polychoric correlation. And then in fact, I did 3 because I know there's, for sure there's 2, but we want to try to always do more than what you think there are. So I tried 3 and then I did I allowed them to correlate in my rotation. And so in the end, I actually did get 3 factors. I think the first factor eigenvalue was around 8, and then it was 2, and then it was 1. So anything, I could try 4 or 5, but the eigenvalues was less than 1. So that means I know for sure now that these 20 questions can be grouped into 3 factors. So once you're sure of that, you can do a confirmatory analysis. When you run that, you will get chi-square, and you also get these fit statistics. So there's two things that measure the incremental fit, which are comparative fit index and the Tucker-Lewis index. And if they are greater than 0.95, that means your model is a very good fit. But if they're less than 0.95 or greater than 0.9, then your model is a acceptable fit. And there are two indices that measures the absolute fit, which are the root mean square error of approximation, and then the standardized root mean squared residual. If they're less than 0.05, then it's a good fit. And if they're less than 0.08, then it's an acceptable fit. So basically, when you run confirmatory analysis, you'll get these automatically from your output. And so this is for my analysis, this is ideally what I thought of before I ran any analysis. This is what, so I would have the first 11 questions loading onto the first factor, so they can be grouped together into one factor. And then the next 9 questions can be grouped into a second factor. But because after I did the EFA, there was a third factor, and I consistently saw that item 19 and 20 loaded onto that third factor. And these 2 factors are mostly asking about fatigue. So the first 11 was asking about cognitive function, and then 12 to 18 was about the physical symptoms. But the last 2 was asking them about fatigue. So that's why there maybe potentially can be a third factor with my questionnaire. And so there's also something else called a bifactor. Oh yeah, I forgot to mention. So these factors can be correlated. So that's why they're called a correlated model. But recently, something called a bifactor has become popular. This essentially is the same as my previous model. I'm just going to use the 2-factor as an example. But there's also a sort of general factor where you can group all these questions into one factor. And the reason why this has become popular is because the residual variance that you see in each question can also be taken up by this general factor as well. So they, whatever the residual variance are now taken up by these two factors, they can be taken up by the general factor. And also, because these questions are used in emergency department for physicians to diagnose patients and things like that, and so they could be busy. So if we could just get a general factor, like a general total score for their concussion symptoms, that might help guide physicians clinically. Yeah. So next is when we fit these factor analysis, an extra step we can do is measurement invariance. We want to measure the measurement invariance because these surveys for my study for our study, we gave the questionnaires to a child and their parent, but we also gave it to different groups of people of kids who had concussion and those who had orthopedic injury, and then we also give them at different times. So then we want to make sure that these questionnaires are measuring what they're supposed to measure to these different, no matter when you measure them and no matter who's answering these questions. So that's where measurement invariance comes into play. And so the first one is the baseline invariance is configural. It's called configural. Basically, so the pattern of factor loading is consistent across groups or time, and then each question should load most highly onto that factor. So basically, we want to see the first 11 factors loading onto the first factor, and then the next 9 questions loading onto the second factor. We want to see that in different groups at different times. And then if that is established, then we can go on to something called the weak invariance. So in this one is where we constrain the loading of each question onto that factor to be equal as well. And so this allows the comparison of the factor variance and covariances. And so which means that the proportion of variance in each question is accounted for by each factor, which is similar in each groups. And after we have established weak invariance, we can go on to strong invariance, which we now constrain the item thresholds. So for my questions, they are categorical. So that's why for me, I use thresholds. But if your questions are continuous, then you can use the intercept. So we constrain that to be equal. And at this time, if we establish that, then the factor means between the groups, the factor means between the groups can be compared, and then these differences in the factor means is a true reflection it's a reflection of the true difference. So for example, if I was to compare the concussion group with the orthopedic injury group, and if their factor if I have established strong invariance, and if the cognitive factor, the mean is a lot higher in the concussion group, that means those with concussion really truly have a sort of severe cognitive symptoms after concussion. So which is something that we do want to see. And after that is the strict invariance. So this, you want to restrict the residual variance for each question to be the same across group. And then in this case, the differences in all the item parameters are entirely attributed to their difference in the factor means. And so you go in this order. Once you achieved the invariance at one level, then you go on to the next level. And you can compare these, which I'll go into details once I show my codes. You can compare these if the CFI, which is the incremental fit, does not decrease by more than 0.01 going from one level to the next, or if the RMSEA, which is the absolute fit, doesn't increase by 0.015. And okay. So to build these models, okay, so for the measurement invariance, this is essentially, I think I'm missing a step. Okay, there. We start with confirmatory factor analysis first. So the package is lavaan, and then you also load the library, psych library, and then you would set up the model. So we want the first 11 questions to load onto the first factor. So this is how I define my model. This means the loading, so the equal sign and the squiggly line. There's several syntax, which I will go through on my next slides. Then we want question 12 and 20 to load onto the second factor. And so that's, I'm only using the 2 factors as an example, but the 3 factor you just add on to the extra one. And then so you fit this model here using CFA, and I put my model in here, and then the data frame. There are estimators and parameterization that you have to choose from, which I will talk about in my next slide as well. And then you have to set whether you want standard level to be true or false. So if it's true, then the loadings themselves will be freely estimated, and the factor variance will be set to 1. And if it's false, then the loading of the first item here onto that factor will be set to 1, and then the factor variance themselves will be freely estimated. Sometimes you might have to choose true or false, depending on whether you have convergence issues or whether you want to be looking at loading or you want to look at variance. So depends on that. And then if there's missing data, then for me, I just use all the completed case. And here I put in something extra called order. If your questions is continuous, you don't need this. But because all my questions are categorical, then I tell R that they're ordered categorical. So 0 being the lowest level to 3 for my questions. And then you can just get a summary. You get all the statistics. You also get, so that fit measures here too means you'll get the fit statistics that I talked about earlier, the absolute and incremental fit. And then you also get loading, the factor means, factor covariance, and then the threshold. You'll get all that information once you just put summary. For the bifactor is exactly the same, and all you have to do is just put in the general factor as well, with question 1 to 20 loading onto that factor. The only other extra thing here, you still want all of this in here in the CFA, but you also want all orthogonal to be true, because you don't want these factors to be correlated, because then you have convergence issues and they're not supposed to correlate. And there's something extra you can do for the bifactor model, which is called the OmegaH. So if you just do reliability and put the model that you just ran into here, you'll get an OmegaH, which will explain the percent of reliable variance that can be attributed to the general factor. So for me, if I had about 80%, which 0.8, which means 80% of the variance in all my questionnaires can be explained by this general factor, which is a strong evidence that this general factor should be kept. And yeah, so it's a level. And so for my estimator, I use the weighted least squares with mean and variance adjusted. This was suggested by almost all the articles I've read for categorical variables. And for the different estimator, there are tons of estimators, and I am not really an expert on what each of these means, but I do have the source down here. And so there's maximum likelihood for the continuous variables, but there's also all these different ones that you can use depending on the nature of the questionnaire. So the one that I use is actually more or less like this, except the estimators themselves has a robust standard errors and scale tested statistic. And because my questions are categorical, and so the best option was to use diagonally weighted least squares. And for parameterization, there's 2 options. Delta is the default, and then there's theta. And if you use theta, it will allow you to estimate the residual variance in each question, which is needed for the strict invariance. If you do delta, you won't get the residuals for each question. But sometimes theta will cause convergence issues, which I encounter. So sometimes I was forced to use delta, because if you use delta, at least you can get to strong invariance. So that still works. And then for the syntax, there's only just 3. So from the previous slide, this was when you have a question loading onto a factor. If you have factor on this factor, let's say factor 1 on this side and factor 2 on this side between these two squiggly lines here, that means you're getting the variance. And if you have a factor 1 and a factor 2 on each side, and then you're getting the covariance. You can do the same for each question as well. And if you want to define the factor mean, you just put the factor and then a squiggly line and 1, and then R will know that you want to estimate the factor mean. So to build the measurement invariance is pretty much you just build on the confirmatory factor analysis. So here is the same as before. You just go F1, first 11 questions, F2, and these questions. For the alternative option, for previously, when I said ordered here, so another way to do this, if you don't want to put ordered here, is you can put that into your model. So you don't have to write out ordered each time you run the model is, oh, shoot. So you can do this way. So for me, because my questions is this from a scale from 0 to 4, so there's 4 levels, 0 to 3, there's 4 levels. So there's 3 thresholds. So if you do this, you don't have to put ordered here down at the bottom when you fit your model. So I have question 1, there's 3 thresholds. Question 2, you could do that all the way to question 20. So then now your model is complete. So this is exactly the same as I did in the CFA earlier. And then, so you want to fit, first you want to fit configural. So then we put the model, so again, it's CFA, you put the model in here, data frame. There should, for me, this is for, so if we're doing the MI of group using the correlated model, there's a variable that I have a variable called group. So if they had concussion, then they belong to one group. If they had orthopedic injury, then it's another group. So there's just an extra variable called group. My estimators and parameterization is exactly the same and missing. And then when you run this, you will, you'll get all the statistics and the loadings, factor means, variance, and all that. And so the next we want to try is weak invariance. So to do weak invariance, all you have to do is just copy everything once your model is defined, that you don't have to do it anymore. So you just, whatever you put in configural here, everything inside, you still need that. The only extra thing is you want to constrain the group that equal loading. So you want the loadings onto the factors between the concussion and the orthopedic injured group to be the same. So this, you just set them to be equal on loading. And then you, same thing for strong, you just have to add an extra loading, extra constraint to equal threshold. So the group, they should have equal loading, equal threshold. And then for the strict, you just add in residuals. So this is pretty, so basically you just have to build onto it. And then to compare, you use lab test LRT. You put in configural weak, and the method is Satora Bentler 2010. There's only 3 methods. There was Satora 2000 originally, and then Satora Bentler 2001. So this is the most updated. I think they did a bunch of trial and error, and in the end, this one is the most appropriate. And once you do that, you get the comparison between degree of freedom, log likelihood. And the ones you want to look at is just the CFA to see if it did not as long as it didn't decrease more than 0.01, or if it didn't increase, if the RMSEA didn't increase more than 0.05, then you have established the the next level invariance, and you can just keep going. The next one you can put weak here, strong, and then run it again. When you run this, you get all these results. So this is for group, and then for the correlated model, for the bifactor model is pretty much the same. You just add in the general factor with the 20 questions loading onto it. Here is exactly the same as the previous. You just have to add in the orthogonal equals true to make sure your factors aren't correlated, and everything else stays exactly the same with the group equal loadings. And so this is for group. So group is simple because you would have each row represent a participant, right? So your data will be in a wide form. you have 20 questions, the score for each question, and then you have a group where there'll be group 1 or 2, depending on the kind of entry. But if you were doing, I also compared measurement invariance between child and their parent, and also time. So I will use parent and child as an example. So if it's a parent and child, that means I have 2 sets of scores. So I have 20 scores across for the child rating, and then 20 scores again for parents. So that means you have 40 scores across. So there's no group variable that you can use to define whether it's the child or the parent. So in that case, if you want to compare measurement invariance, then you have to build both parent and child into your model. And here's what I mean by that. So this at the configural level, so when you have 40 scores across, then you have to say, let's say first factor for the child. So the first 11, so the 11 questions, question 1 to 11 that was answered by the child will load onto that first child factor. And then question 12 to 20 that's rated by the child loads onto the second child factor. And then you do the same for the parent. So that's when you so this is when you first build the factor loading. And then you write the threshold, which is the same as previous, but you now have to add a separate threshold for each parent and child for the 20 questions. You can put them on separate lines, where you can put them on the same line with a separated by semicolon. It will all work. Next, you actually want to set the factor means, because so factor means, you want to set one of them to 0. So either the parent or the child can be 0, and the other one can be 1. 1 means factor means for the estimator. So it's not a factor mean equal to 1. So this squiggly line 1 means we want the factor mean. So this setting 0 means we don't want this to be we want the child to be 0, so that we can see what the parent factor mean will be like. So for comparison, you can switch them. You can have the parent mean equals to 0 and the child mean to be freely estimated. And then later next you want to do the residual variance for each question. So you want that. So this is the residual for each question for the child and the parent, again, child and the parent, all the way to question 20. And then you want to do the covariance between each question for the child and the parent all the way to 20. And the covariance of the factors themselves will be automatically estimated. Why does this? Yeah, so for the previous one here, everything that I mentioned, this will be automatically estimated just from this when you do group. But when you do between parent and child, then you have to actually build all of this from scratch. And then here will be the same. You just do the CFA, your entire model, the data estimator, parameterization missing, and you can do a summary, fit measures. You get everything here plus the fit statistics. So this is the configural level, so the most basic level. Next, if you want to, when we want to do weak, we have to constrain the factor loading. So here I have constrained the factor loading for the first question onto the first factor is the same between the child and the parent. So the second question onto the first factor, same. So you want to do that for the first for all the questions. Here it can be any number, any series of numbers or letters. It doesn't have to be A1. You can do A, B, C, D, E, F, but whatever is simple, as long as these two are the same. The first question for the child parent onto their first factor for the child and the parent, as long as they are the same, these letters and numbers are the same, then R will know that you want to constrain them. So here I want to, for the second factor as well, question 12 for the child, question 12 for the parent, it should be the same loading. The loading should be the same onto the second factor and so forth. And so everything else stays exactly the same. We only want to constrain the factor loading at this point. And when you run this, it will be still the same as before. And then you can do the lab test and compare them to see if the CFI, how much the CFI changed and how much the RMSEA changed. And so next one is, once you have established that, then you want to move on to strong. So you keep the constraints that you previously already set. Now you want to constrain the threshold. so for me, so I have 4 levels, so there's 3 different thresholds. So each threshold is the same between the child and the parent. So the first threshold should be the same. The second threshold for the first question between child and parent are the same. And you want to do all that to question 20. And the threshold between each question should be different though. So the first threshold in question 1 should be different from question 2 or 20, things like that. And everything else stays exactly the same. You compare these two. If you have established strong invariance, you will move on to strict. And so you still keep everything from you've done before. And all you have to do now is restrict the residual now between each question. So the residual for question 1 for the child should be the same for question 1 for the parent. And you do that to question 20. And then you compare. And then once you have strict invariance, that means you have to achieve the highest level of invariance. That means your questionnaire is very valid between the parent and child. And so for the bifactor model is similar. And the only thing you want to add in is the general factor. So we want a general factor for the child for all 20 questions, and then the general factor for the parent. And then you just add in the factor mean again. So all the factor means for either the parent or the child should be 0. You can choose one, and then the rest should be 1, I think. Oh, yeah. And then the rest should be freely estimated, so you can compare. And the only other difference, previously I've mentioned that covariants are automatically estimated, but you do not want the factors within a parent or within a child to be correlated. So you want for example, the general factor and the first factor within the child to be 0. So then, because those are automatically estimated, you actually have to set them to be 0, so that R knows to not estimate them. So then the general factor to the first factor within child should be 0, then the gen to the second factor first and the second. So you want to do that for the parent and for the child. Otherwise, you will have convergence issues. And and then when you fit the model, is exactly the same configural, and then you do the summary and you get all the fit statistics. And the next one, so here's the same, you restrict the loading, and now you just have an extra line that you have to restrict. So questions 1 to 3 to 20 loading onto the general for the child, the loading should be the same for the parent as well. So yeah, so these numbers are the same, and everything else still is exactly the same as your previous model. And you just run the model, you compare them. Once you've established week, you go on to week, which is exactly the same as the correlated model from before. The threshold are to be the same for each question between parent and child, and everything else still stays the same. And then you do a lab test to compare. And if once you establish strong invariance, then you just move on to strict, which there's no, it's the same as before when you restrict the residual between each question between the parent and child to be the same. And so that's pretty much for the coding parts. And so to keep in mind, some of these models, some of my models became really complex, especially with time, where I fit in 3 different times. So I had to do, so from the previous, so there's even more parameters and model building you had to do. So those took up to 5 hours to run. And they will always run into convergence issues. And I find if you just put in the warning message into Google, you usually find some kind of solution. But if that doesn't work, you may have to use delta instead of theta, like I mentioned previously, or you may have to set more restraint from the baseline. So for example, here, ideally, we want this to be all freely estimated. But if you do have convergence issues, you may have to already start setting constraints right from here. So for my models, I had to actually set the factor loadings, 2 of the factor loadings, restrict them to 1, and then here I also had to do some kind of restriction as well. So you kind of have to play around until you actually get your model to converge. So the more freely estimated parameters you have, the more convergence, the more likely you have convergence issues. But it's okay to have constraints in the beginning as long as they stay consistent, because you just, and then once you add more constraints, yeah, so that part is fine. And then, so for my results, the bifactor model did show a better fit when the model is complex. But when I did the simple CFA in the beginning, the correlated model was much more parsimonious. And yeah, and they were easier to converge as well. So, and I also find that if your questions are continuous, then I think you have an easier time with conversions as well. And because for me, I also have missing data as well. So those are all asked into the model complications there. And yeah, so that's pretty much the topic itself. And I just want to thank all the PIs for supporting me here. And yeah. And thank you for listening.
That's a great presentation.
Not confusing.
No, I see, Pablo, you have a question there. I'll prompt you in a second. I learned a lot because most of the work I do is either around, like, we do a little bit of like survey analysis or questionnaire analysis. And I think we've always struggled with really, like, if we're just throwing into regression, we usually just PCA and call it a day. But the methods that you're showing are much more disciplined. So I do appreciate you sharing that methodological process of going from, casual to strict. So I do like that. I've learned a lot from that. So thank you very much. Pablo, can I prompt you, since you've asked a question on the chat? Do you mind asking to see if there's something from there?
Sure. Thank you very much for the presentation. Excellent. Just curious about this package. It seems very focused on what field is it focused on, or is it general? Is it just ANOVA analysis, or is it more focused on healthcare?
I would say anything. For me, psychology is more for if you have questionnaires, raw questions, yeah, and you want to be able to group different questions into sort of like a common theme, like a common factor, because you don't want to be using all 20, however many questions you have, because you don't want to be using all those raw questions into a regression analysis. So this package, yeah, is mostly to use for factor analysis if you want to.
Thank you very much.
Yeah.
Is it possible to see some sample output from running the lab test?
Actually, I think it's fine. Yeah. Let me just. Yeah. So here, for example, is the correlated model between the parent and child. So the more complicated one that I showed. So COG is the cognitive symptoms. This is for the parent, because I have 3 different time points. So this is at post-acute. So the SOM is the somatic, and then this one's cognitive for the child. So these ones are my question numbers. So this is actually just question 1. So yeah, so I had question all the way to 11, and then again from 12 to 20. Let me this part here. Track that. Yeah, there we go. And then yeah, so the 2 factor. This is the parent. This is for the child. And then here is the threshold. You could also just do ordered equal and then brackets, and then all your question numbers down here as well. But I just set here so that I don't have to enter that each time. So this is just question 1 for the parent, the 3 thresholds, and then question 1 for the child. So the child, so HBI is the survey name, and then P is the parent, PA is post-acute, and then 1. So then I do it all the way to 20, and then because I had convergence issues, ideally you want this to be freely estimated, because I think I had convergence issues, so I had to set them all to 0. So to converge, sometimes you will have to set these constraints, and then yeah, so you just run. So this is what I named my model here. Correlated, configural at PA at post-acute. So here, I'll put that in here. That's the model name, the data. This is my data name. I use the estimator, missing, standard level is true. It can be false, depending on if you want the variance to be estimated or not, and then you do a summary, and then here's what you get for the result. So you get all the statistics here. You get the so the estimator that I used is yeah. So this one, this is just the adjusted. The one that I use is just the adjusted scale. So you do have the robust, but this is the method. And I would just look at all of this, degree of freedom, my p-values, and all of here. And so this is the models I use. This is if this was just the baseline if nothing was set, like, but yeah, anyway, this is very complicated for me as well. So you just want to look at here. This is your test the statistic. So here you have the CFA, the TLI that I mentioned, the incremental fit, and then here is the RMSEA, which are the absolute fit. And so yeah, if this is over 0.95, then it's a very good fit, so that your model, your factor definition is good. And then if this is less than 0.05, it's good. Less than 0.08 is acceptable. So here I have achieved acceptable fit. And then you also have the SRMR, which is 0.05. So for me here, it's close to good. And then you get all the factor loadings here as well. So this is the factor, and this is the each question loading. So yeah, so you do want to see these. If you want, technically the standardized, the highest loading is 1. And then because I didn't specify to get the standardized, but if you get standardized, you can you get an extra column here with all the standardized values if you want to specifically look at loadings. But this is showing me that everything is loading strongly. The first 11 factors on first 11 questions onto the first factor, and then next 20, the next 9 questions onto the second one. This is for the parent. This is for the child. And then you get the covariance, which is the one that I set in my model, covariance between the parents and the child from question 1 to 20. And then the covariance for the factors themselves. And then you have the intercept. So this is the factor mean. This is what I got here. Oh, okay, never mind. I guess I did estimate the factor mean for the child. So we can compare to see. So basically this means compared to the parent, the child rated themselves lower in their cognitive symptoms. And in terms of somatic, compared to the parents, the child rated themselves to be higher with their somatic symptoms. You can compare these between groups and different times as well. And the rest all should be 0 because my questions are categorical. So instead of using intercepts, I have thresholds. So here, I already set some constraints here because of convergence issues. Technically, these should not be equal at the base level. But if you have convergence issues, then you will have to set extra constraints. But you'll get generally get thresholds here. I don't really look into detail too much with here because when you do factor now, you just want to compare if you have the invariance. And then you have the variances themselves for each question. So this is the residual for question 1, 2, and then yeah, for the parent and the child, and then the variance for the factors. And then yeah. And then there's all these other outputs too. So yeah, that's pretty much what it looks like. There's a lot, and most of the times, unless you want to really examine all of this, if you just want to, if the goal is just to see if the questionnaire is consistent between different raters or different groups, then if there's no obvious errors, then you can just compare to the next model. And yeah, I hope that helps.
Thank you, Cherri. It's really interesting. Thank you very much for showing us this.
That's a good question. Thanks, thanks, Pablo. I see you have a question here. Do you want to ask that yourself?
Sure. Hi, Cherri. I wonder, there is two different cameras. So we have the psychometric package also available in R, and I wonder if you had a chance to take a look at it and see. Seems like psych package is pretty capable, but anything else that is extra in that package, if you know.
I know there's most of the factor analysis are done in M+, so I'm not sure if you have heard of that, but I don't really know the psychometric package itself, but I know there's there are definitely other packages that you can use, and there's one that can sort of almost copy what M+ does, so they can imitate. But I've tried it, but it didn't really work for me. So ideally, most of the examples when I'm doing factor analysis, they were all done in M+. I guess is they have less convergence issues, but because I didn't have M+, and I tried to use that package that you can mimic M+, but it didn't really work for me. So I found this one worked the best. Yeah.
Okay, thank you.
Well, those are two great questions. I think for those that stay to the very end of the presentations, I find that the answers from the presenters like Cherri today gave so much additional color and flavor. I was going to ask about the differences in how parents and children evaluated it. It's like the parent syndrome of thinking that your kid is like amazing, or or like just not knowing truly what the I guess the child is experiencing. So you answered that question, so that was great. So thanks, Cherri. I don't know if I don't see. Oh, Byron, I think I saw your hand shoot up briefly. Do you mind if I?
Yeah, sure. I got a quick question. So I think Cherri, you mentioned like, well, I guess number one, were you running sort of like your models like on your personal computer / laptop kind of thing, or because you mentioned sort of like longish times to get your models kind of finishing or completing their run. So just wondering if you tried to like explored ways to try to like speed that up at all.
Yeah, because we're all working from home, so yeah, you have a computer at home. I have an iMac at home, and so actually I was just sometimes I'll be running them, and I'll go eat dinner and do my stuff, and I come back and then wash the dishes, whatever, and I come back to get the results. I think because my model is too complex at one point, because I had to build 3 different time points, and I added in all the covariance, variance between factors, between questions, and if I just do the simple confirmatory factor analysis, it was pretty fast. But the more complex the model is, the longer it takes. And I'm not sure if I found a way to reduce that, because yeah, I don't know if you have any ways to reduce the time.
Yeah, I don't know. Probably people have a little bit more experience like in that area, I guess. But I don't know, like, yeah, off the top of my head, if there's pretty like standard ways to maybe speed that up a little bit.
Yeah, I was pretty shocked too, because I mostly used data before this, and it never takes this long to run something. But I think this just, because even today I was trying to run some latent class analysis using random effects, and it was taking 6 hours. And yeah, so I was shocked when I first started using R that it would take this long to get results. Yeah. But yeah,
No, that's a good comment. That's probably something, Michelle, that we'll probably have to schedule for someone from an optimization perspective. But because I can see how multiple times would just exponentially increase the workload on that.
I want to know too how to decrease that convergence time as well. So yeah.
Awesome. So I guess on that note, that's a great transition out of this presentation. Thank you, Cherri, very much for your generosity and your time in preparing this, not to mention all the work it took you to actually process the work. So thank you. We're always looking for great presenters like Cherri today. So if you have a topic, perhaps optimization, please feel free to reach out to any of the organizers, and we'll be happy to have you come in. But with that being said, thank you very much for coming today. Big applause to Cherri. Thank you very much for sharing your knowledge with everyone here. And I hope everyone learned a lot, because I definitely did. So yeah, with that in mind, thank you.